So let's finish just a few more examples from chapter 11, section 4, about the colligative properties. Those properties that change when we make a solution. Okay. But one of the things that we learned was a new type of concentration called molality. And I do think that you should be able to convert between all concentration unit types, okay? Percentages and molarity and molality. So this problem is converting a given molality concentration to a concentration unit of molarity. Okay. So first thing we got to remember is when it gives you a molality, the 33.7 molal nitric acid, what does that actually mean? Break it into the two parts of the fraction. That means there's 33.7 moles of solute. In this case, the solute is nitric acid. Okay. Per what? 1 kilogram of solvent, which in this case is water. Okay. What else are we given in this problem? What is that little symbol D? Okay, that is the density. You're given the density. The density of what? Of the solution. That is not the density of water. That is not the density of nitric acid. That is the density of the solution. So you are given the density. (1.35 grams of solution per 1 milliliter of solution. Okay. What's the molarity? What units do I need to end up with in a fraction? Moles specifically of solute per liter of solution, not of solvent, but of solution. So you got to pay attention to the unit and the label of what we're trying to find here, all the parts. In order to get volume of a solution in some way, I can use this density, right? If I know the mass of solution, I can get the density. I can get the volume from the density. But I don't have the mass of the solution. What do I have? The mass of just solvent. But what is a solution? What is the mass of solution? The two added together. You take the mass of the solute, unless you're told differently. But we're not told anything differently here, so this is what we have to go by. The mass of the solution is the mass of the solute plus the mass of the solvent. What mass of solvent can I say I have? Okay, so I got 1 kilogram. Or 1,000 grams, right? Solute. How can I get the mass of solute that would be in this concentration? Let's take those moles. And let's convert it to grams using molar mass of HNO3, which you would have to go add up for yourself, right? 15, 48, 63. Grams per 1 mole, right? That gives 2,120. What did I get? 3.7. Blah blah blah. How many sig figs should this gram amount represent? 3. 1, 2, 3. Okay. So I'm going to do this grams plus this grams equals 3,123.7, blah, blah, blah. So that's the mass of my what? It's my solution. Okay. What can I do now? My goal is to get for the solution volume. Now I can use the density. Now I can use the given density of the solution. What needs to go where? Grams has to go on the bottom so that I end up with volume in the numerator. And I don't want milliliters of solution. I want liters. Okay. That's what I got. 2.3139, blah, blah, blah. So I got some more stuff after that. 3 sig figs, liters of solution. Right? Okay. Molarity, again, moles of solute per liter of solution. If this is the volume of solution, what's the moles of solute? It's that amount that was given in that. That's the amounts we were working from. So that's the amount of moles. So the molarity, moles per liter. .6 is what I got. Y'all check if you got the same thing. Good. So I know there's at least one homework question that makes you change between these units in that second set for chapter 11. Well, you have to do that on the test. Yeah, probably. Probably will. And then the other one I wanted to look at was, I think, I wanted to look at 25, the very last one. So this was looking at the colligative property of osmotic pressure. Okay, so we talked yesterday, we finished up our chapter 11 talking about these 4 types of colligative properties. Vapor pressure lowers when it's a solution. Boiling point increases as a solution. Freezing point depresses. And then there's osmotic pressure, which is the pressure difference between two sides of a semi-permeable membrane, right? And I said, I don't need really you guys to understand what osmosis is or give me a definition of osmosis, okay? You need to understand that your solvent moves towards the side that has solute because it's trying to equal it out, dilute it out, okay? And when you have movement from one side of your membrane to the other, you end up with two different volume levels, right? And that difference in volume levels is essentially what becomes osmotic pressure. Okay. So this pressure equalizes out when you get an equal flow rate. Initially, there's a lot of flow this way from solvent to solution side, but eventually it kind of equals out and you just get an even flow back and forth. But one side, the solution side, has more volume than the solvent side. We can calculate this osmotic pressure using this equation. Okay, so you guys tell me, remind me, what is I? When I say it's the Van't Hoff factor, what does that mean? It is the number of particles that that solute splits into, dissociates into. Tell me how you know how many particles something splits into. If it's an electrolyte or not. If it is a non-electrolyte, that means it's covalent. That means there's no ions being formed. How many particles does it form? Just one. How can you recognize if something is a non-electrolyte if I don't use that term, non-electrolyte? Guys, if it's a covalent compound, if it is not ionic, we're going to assume it's a non-electrolyte. If it's not an ionic compound, it's a non-electrolyte. Okay. If it is an electrolyte, then how do you know how many particles it splits into? The number of ions that it contains. Or you can actually calculate this I value. And so some problems in active chem will give you a calculated value to use. Use that value. Okay. I'm not asking you to ever calculate the I value. I would only ask you to estimate it by counting the number of particles. Then we need molarity, and then we need temperature in Kelvin because we're using the gas constant R. And because we're using a gas constant, because we're talking about pressure, all temperatures have to be in Kelvin. Liters and moles, that's why we're using molarity. And what is our pressure, this osmotic pressure, going to be calculated in what units? It's got to be atmospheres. If you are given an osmotic pressure in a unit other than atmospheres, torr, kilopascals, what do you have to do to be able to use this equation? You have to convert your pressure, your osmotic pressure units from torr, whatever, to the unit atmospheres. You have to do that because you're using this R value that involves atmospheres. Okay. All right, so this was what I wanted to do. Not this one. This one. So this is number 25. Okay, 0.5 liter sample of a solution that contains 10 grams of hemoglobin. Let's try that again. Hemoglobin. Hemoglobin. Y'all know what hemoglobin is? It's this big ass molecule. It's like huge. Okay. It's a big molecule in our blood, and it actually carries around oxygen. It has iron in it. The oxygen attaches to the iron that's in the very center of this molecule, and that's what carries the oxygen around in our bloodstream. Okay. So hemoglobin, I'm going to dissolve it in some water. Here's my atmospheric pressure. Here's my osmotic pressure. 5.9 torr. Okay, so here's what I was talking about, right? I have to have my pressure in units of ATM. Okay, so I'm going to have to convert that. At 22 degrees C, I'm going to have to convert that, aren't I? Kelvin. What is the molar mass of hemoglobin? What is the piece of my osmotic pressure formula that I should be trying to solve for if I'm wanting to get to molar mass? I have to solve for the part that involves a mole, right? I need moles to calculate molar mass. So in this equation, that means solving for the molarity first. Okay. Just like yesterday in the lab, what was the piece we had to solve for to get molar mass using freezing point depression? That molality, because that was the thing that involved moles. That's what we got to do first. So here is our rearranged osmotic pressure equation solving for molarity. Do that first. Say one more time. There is, we don't calculate osmotic pressure with molality. It's only molarity. It's only molarity. This was freezing point depression, not osmotic pressure. Okay, so you guys should be able to manipulate this around, convert those pressures and that temperature, and let's solve for molarity. Yeah, let's try that. How do you convert from torr to atmospheres? Remember the conversion? Huh? 1 atmosphere is equivalent to 760 torr units. 760, right? So if I have 5.9 torr, we're going to divide by 760 and get our atmospheres. And then I'm going to take my 22 degrees Celsius and convert that to Kelvin. Okay. 0.00776, blah, blah, blah. Okay. And that is 295.15 Kelvin. But we would actually stop at the ones place because that's where our measured temperature was precise to, was the ones place. So we're going to solve for our molarity, taking the osmotic pressure divided by, what about I here? It is absolutely 1. Hemoglobin, while it does have iron in it, is not an ionic compound. It is not splitting into, dissociating into smaller particles. Wouldn't that be terrible if it did? Okay. So we can assume I has a value of 1. So I don't need to worry about it in my calculation. Okay. Pressure divided by, which R value do we use here? Yeah. The universal gas constant with joule units is the 8.314 number. The constant with atmosphere units is 0.08206. Yes. Okay. Okay, so 3.205, something along those lines, times 10 to the -4th. Very small molarity. Very small molarity. Again, how many sig figs am I keeping track of all the way through? 2. That original pressure only had 2 sig figs, so that I'm tracking those 2 all the way through. So this means what? Molarity means what? Molarity means this number of moles per 1 liter of solution, right? That's what that means. If I had 1 liter, this is how many moles I would have. But I don't have 1 liter. What volume do I have in this problem? I have half a liter. So I'm going to multiply my molarity by the volume that I do have, right? God bless you. God bless you. This, all I'm saying is I'm multiplying these numbers, and so as a fraction, that's just over the number 1. If you want to, if you feel like you need to fill that in with that space in with something, it's just the number 1. And then, how many moles is that? Still a very small number. 1.6 times 10 to the negative 4th, basically. Yeah. Okay. So then how do I get the molar mass? The moles that we just calculated. Loretta? There we go. I'm just going along with whatever you say. Now, how many grams of hemoglobin did the problem say we dissolved? I think 10? 10 grams. 10 grams divided by this number of moles that we just calculated. Using what? What colligative property did we use to calculate moles here? We used that osmotic pressure to figure out the number of solute particles. Number of moles of solute particles. That's what we used. Guys, this molar mass should be very large. Okay. Hemoglobin is a very large molecule. It should have a large molar mass. What'd y'all get? 62,000. How am I going to write that in scientific notation the best way? 6.2 times 10 to the positive 4th grams per mole, or, oh no, just grams per mole, sorry. Grams per mole, right? Bueno. Okay. So, yes, I have decided that this is the end of 11 for us. Okay. I am not interested in us going through colloids. I'm not interested in asking you questions about it. I'm just not interested. I'd much rather get started on our next chapter, which is one of my favorite chapters. It's about this thing called kinetics. If you were so interested, of course, you are free. Once I email y'all this PDF, since we can't get it to open in Blackboard, you are free to read about what is the difference between a solution and then this thing called a colloid. A colloid is like a solution, but it's just bigger particles. I mean, that's what it is. You can certainly read through it. but I'm not going to test you over it. Okay. So let's let me go grab the new chapter 12 stuff off the printer. You guys can get the chapter 12 slides opened, and we will get started. So if you take a little break now, if you need to go to the bathroom or whatever, let's do that now. And then we'll start kinetics when we get back.